This is minutes studying and GPA. So we got Bob's minutes studying, let's say, in a week and his GPA. Edna's minutes of studying in a week and her GPA, and so forth. Looking at the data set, look at the data set. What do you see there? Do you see a trend at all? Do you see, is there something that you see here when you look at this data set? And feel free to take a look at it for a moment. So those of you who might be familiar with correlation already are saying a positive correlation, okay, or a correlation, all right, which is good. So what we see here, okay, if we rearrange it, it'll be a lot easier. We can see that that as the number of minutes go up, so too does the GPA. So Erica, who studied for 178 minutes in the week, has the highest GPA among the people here. If we were to graph this out, if we were to make a scatter plot, and understand what a scatter plot is. Scatter plot is literally the dots being there. It kind of makes like an upward line here. Kind of makes this upward looking line that on the x-axis, which is the horizontal row, as it goes up, on the y-axis it goes up as well. So it's a line that's trending upwards, okay? Here's another fictitious data set. We have minutes spent exercising per week and the mile time. Okay, and for simplicity, rearrange it according to the amounts of exercise, minutes of exercise per week. What do you see here? The mile time is in minutes, so 6.5 minutes, or 6.5 minutes would be 6 minutes 30 seconds. Doesn't have to be but you still get the values. What do you see here? What do you see when you look at this? What do you notice in this data set here? Give you a moment to take a look at it. And yes, some of the names were corresponding to popular media, Mo, Larry, and Curly. Do we see anything here? Oh, I'm sorry, I missed, let's see. Negative correlation, right. So yeah, basically what we're seeing here, and again, if you're not familiar with correlation, I understand that. Some people might not be at that point yet. What you're seeing here is that as the number of exercise, or I should say, as the minutes of exercise increase, as the number of minutes of exercise increase per week, the mile time goes down. So as one variable goes up, the other one tends to go down. If we were to make a scatter plot of this, it looks something like that. Okay, notice that it's a downward line. Okay, it's a downward line. So I go. We have another fictitious set of data here. This is a hypothetical scale called the friendliness scale. How friendly are you on a scale of 1 to 10? And a person's shoe size. So let's rearrange it according to the friendliness scale. What do you see here? What do you see here? You see no correlation. Another way of asking is, do you see a relationship between the variables? Do you see a trend between the variables? And for those who are not familiar with the term correlation just yet, the big question is, do you see a trend? Do you see something, as it were? And it doesn't seem to be, right? There doesn't seem to be any trend here, as it were. And by the way, if you have questions, please put them in the chat. I'm happy to answer them. If you have questions for the chat, we do address questions. If there's a lot of questions, I'll start using the, ask a call to action thing where you can ask questions there. But for right now, you can put them in the chat. So if I were to take this friendliness, shoe size, these numbers, okay, and I were to make a scatter plot of that, you're going to see I have really nothing to speak of here. I mean, there's no real nice line you can make of it like you could those other ones. So in that same spirit, let's look at some other things here, okay? Do you see a line maybe that tends to go upwards or downwards? I know it's not necessarily very clear. Do you see could you kind of fudge a line where it might go in a certain way? Does it trend upward? Does it trend downward? So it does have a negative slope. It tends to go downward. It's not very strong, but it's certainly there. At least it's not as strong as some of those other ones that we see. I think. the line of best fit here? Can you draw with your finger? Can you draw something where it's the line of best fit? What do you think about that one? Maybe upwards, downwards, not at all? I would say nothing. So to answer about the correlation coefficient, we're going to answer that in a little bit. But the answer, I think if you're asking, would this be close to zero, the answer would be yes. But we're going to get to that a little later on. So yeah, you can't really find a relationship here, and neither with this one here. I don't think you can find a very good line of best fit here, okay? So to Lori's question, yes, this might be a correlation closer to zero. Here, what about this one here? What do you say for this one? And no, we're not going to be looking at scatter plots all night. This is not the plan here, just so you know. But so looking at this here, do you see a line here? Is there a trending line, as it were? Looking at this, does it seem to go in a particular direction? Does it seem to suggest a certain trend overall? Does it go upwards, downwards, in a positive direction, negative direction? As the x-axis increases, okay, what happens to the y? Yeah, I'd say it tends to go upward. And you will, at some point, on the AP exam, it is a fair question to be given a scatter plot and identify the actual correlation there. I will tell you that they will be much easier to the exam, but still pretty easy to eyeball. This here is looks kind of tricky, but it's actually, you're looking at this, it won't be as tough as this on the AP exam. And I'll tell you this right now, it tends to go in the upwards direction. The reason why is because you see a lot of dots clustered sort of in the middle that kind of suggests an upward trend. Again, this is, that's a pretty difficult scatter plot there. I'll give you an easy one. Here's an easy one. How about this? Does that seem a little easier, maybe? Just maybe? Or it's strong, not only it's, I would say it is about that. And here, this would be -1, okay? And if you're not familiar with these numbers, we're gonna go over them in just a little bit. So, all right, so let's kind of go into a little bit more detail here. When I'm talking about two variables, okay? And when I say variables, they could be anything that basically I can measure and gives me a number. Height, weight, your mile time, how happy you are, how much you love AP Psych, blood pressure, anything that can be quantified. Anything that can be made into a number and has variation becomes a variable. So if I have two variables and I want to know how do they, if I'm interested in that particular question, then what you do is you are essentially asking about the correlation. Correlation basically is a word that means relationship. What is the relationship between variables? In other words, how do they relate? I don't mean like a relationship with one's date to the prom or something like that. It's not like they say, hey, I want to start a correlation with you. No, it doesn't work like that. Correlation means relationship between variables. How does one change? How does one change as the other changes? Okay. So we have a question here. Let me just see if I can answer it. So it's correlation and causation. Okay. So this question is from Dylan. If I do not answer this question, when I get to correlation and causation, remind me, because it is a question I will be able to answer, sort of, to an extent anyway. So, and since I'm not, since I don't do AP research, I can't really address it specifically in terms of what they're looking for, but we'll get to that. So, thank you for the question. So, how do they relate? When I'm talking about correlation, there's essentially three possibilities here. Okay, the first possibility is that as one variable the changes in the same direction. So if A goes up, B also goes up. If A goes down, B also goes down. That's one possible change. A second possible change is that as one goes in a particular direction, the other one goes in the opposite direction. So in this case here, as A goes down, B might go up. On the other hand, if A goes up, B goes down, that's sometimes referred to as an inverse relationship. So we have two possibilities there. And a third possibility is that they just don't relate at all. Okay. Examples of A and B. Good question. So for the top part, as one goes up, the other goes up. As the amount of exercise you get in a day increases, how good you feel about yourself also increases. That'd be an example of that. The less you exercise a day, the less well you might feel about yourself, let's say. An inverse correlation might be as the temperature increases, the amount of fur coats sold goes down. That would be an example of an inverse correlation or inverse relationship. As the number of fur coats increases, the temperature goes down. So that's what we mean by examples of A and B here, okay? Or there's just no relationship at all. Your shoe size and how much you like the TV show Grey's Anatomy, okay? Chances are there's probably not much of a correlation, if anything at all. So to answer your question, Agatha, yes, this is where we kind of get into these terms now. One is the positive correlation. When we talk about the positive correlation here, positive correlation means that they both change in the same direction. They both go in the same direction. And when you look at this in a scatter plot, which we'll look at later, you will see that they go in an upwards. And if it's inverse, that's where we get the term negative correlation. As one goes up, the other goes down. As one goes down, the other goes up. When you look at that scatter plot, it goes in a downward direction. And we'll look at a scatter plot later on. And if there's no relationship, we simply say that there is, well, no correlation. Now, this is something that confuses the living daylights out of psych students. And it's these words positive and negative. And we use these words positive and negative to describe a lot of things. And we're talking about positive and negative. When we say direction of the relationship, we are not talking about good and bad. We are not meaning good and bad here, okay? Because you can have positive correlations that are bad. The more CO2 is released into the environment, the greater the risk of global or climate change. There's a positive correlation, but not good. Negative correlation, negative correlation can be good. So the more you exercise in a week, the fewer days you take off. But surely a good thing. So we're talking about in positive and negative has nothing to do with good and bad. Okay, they are two totally different things. So again, correlation is a measure of relationship. And this is something we have to remember because when it's relationship, we have a human fallacy. It's literally one of our cognitive fallacies to see a correlation and start to think that there's a causal effect to it. Where because there's a correlation, we must assume, oh, well, one's causing the other. And it might be possible. But you cannot simply conclude that related that A causes B. You can't make that assertion. You can't make that conclusion anyway, at least based on the data. So, and I can tell you this right now, on at least maybe 3 or 4 written portions of the AP exam, the FRQ, it has assessed to that particular idea. And why not? And I'm going to give you an example. You see, here's the thing. It doesn't mean that correlation is automatically not causation. It means that you can't simply conclude from there that it has to be a causal relationship, or it has to be a causal thing, that A is causing B. Okay, and I'll give you a good reason why in just a bit. Is the word causation a forbidden word? No, because you can use methods where you might be able to infer causation, which we'll get to a little later on. I'll talk about that in a little bit. So I'll give you an example why inferring, when I say infer, it means concluding or automatically assuming, why inferring causation is not advised. Because I can point out to very strong correlations that are not causal, okay? Consider a monthly report of forest fires and ice cream sales in a month. We can see that in months where the ice cream sales are low, there are very few forest fires. And in the months where the ice cream sales are very high, there are a lot of forest fires. So maybe you have a well-meaning mayor or township council or wherever you live, committee of people who say, you know what, we got to save the forest, we got to save the trees, and we have to ban ice cream sales. Because if we ban ice cream sales, it will save the forests from fires. It's a ludicrous assumption, and because it just doesn't make sense. But if you have a correlation, it's interesting to at least look at it into greater detail. Why is it that these two correlate? Well, when I look at this, I say, okay, is it causal? There are several possibilities, okay? I can bring up two possibilities. One, maybe the ice cream sales are causing the forest fires. Maybe the fact that I get my chocolate soft serve cone with a chocolate dip in it somehow makes me so excited that sparks come out of my ears and it ignites trees to catch fire. Ridiculous. Makes no sense. So here we have an example of A perhaps causing B, which is not plausible. The other possibility is that the forest fires are causing the ice cream sales, which is equally ridiculous. That, oh my gosh, the forest is burning down, let's go get a sundae to celebrate. Makes no sense, okay? So the question here is, and this is for you, why then is there this relationship? Why is there this relationship here? Why is it that, why do you think there is this strong correlation? Could be a coincidence, okay? And that does happen sometimes. It's not coincidence here. Dylan says it's hot outside. Desire for cold treats caused by warm temperatures. And if you know anything about forest management, anything, when do most forest fires happen? In the summer. So there's a third possibility, in which case the forest fires and the ice cream sales are caused by a third thing, the climate. In a hot climate, it's drier out in the forest and it's more likely to catch on fire. When it's hot out, more people want to buy ice cream. And so what happens here then is that this relationship, when you factor out or factor in climate, it disappears. In other words, you realize, oh, geez, well, really, there's something else causing them both. So there's no actual relationship here. Now, there's a term that we use. Some textbooks call it an illusory correlation, like illusion, okay? The term I use is a spurious correlation, and as far as I know, both are acceptable terms. A spurious or an illusory correlation, it's where a relationship appears to exist, but it really does not. It seems to exist, but it does not, because either A, it's coincidence, as Agatha suggested, and I'll show you an example of coincidence later on, or B, there's another variable, in this case, something else that's causing both A and B to occur, variable C that's causing both, in this case, climate. So let me ask you then, and I did talk about this in the previous stream that I did, what if I find a correlation, a relationship, and I want to find out if something causes it, or if it is causal, what should I do? What should I do? What should I do? I will answer your question, Agatha. What should I do to infer causation? If I can. And Audrey says an experiment, and you are absolutely correct. The experiment, for our purposes, is the only method that allows us to infer causation, because you are controlling variables and hopefully just manipulating the independent variable that should cause a change in a dependent variable, hopefully controlling everything else that you can. Now, Agatha asked a good question. Is the third variable a confounding variable? Confounding variable, we tend to, in AP Psych, we tend to use confounding variable with experimental inquiry. In other words, it's something that's affecting the dependent variable in addition to the independent variable, or it's affecting the dependent variable, whereas the independent variable is not. It is, I wouldn't necessarily call it confounding, although if you put that on an FRQ, they would probably be okay with that, because it makes it appear, it misleads. It makes you think there's a relationship between two variables when in fact there's not. I guess, so here, Dylan asks a question, could something be causal if you have a really strong correlation? Really, you have to use an experiment to figure that out. There are some statistical techniques where you can perhaps factor out other variables, but that's pretty advanced, and I'll tell you this right now. Some of the people who read the AP Psych exams won't even understand those techniques. If you start talking about that, you're not going to score points for it because you really have to understand regression and control over variables, which doesn't go in there. So for our purposes, you're going to say you have to really, for AP Psych purposes, do the experiment. So now can causation be 100% certain? Are you talking about when you do an experiment, Dylan? I'm going to ask for clarification on that. So after an experiment, so you do an experiment and you have, you find this effect, and maybe there's a confounding variable, and maybe there's some lurking variable that is affecting the outcome, and maybe you know it, maybe you don't. There's always going to be some uncertainty in science. There's always going to be, you can't observe every single relationship or every single phenomenon out there. You just can't do that. It's impossible. Okay, you have to kind of look at, instead, you look at the data that are there and you say, okay, did I do my best to control the variables? Maybe I did, maybe I didn't. So it's not always clear, okay? So maybe I do an experiment. I think I controlled all my variables quite well. Maybe I did, maybe I didn't. I don't know. So is anything 100%? No. But if you do it well and it's being replicated in different labs and it's being affected over and over and over, then sure, maybe you're onto something, but it's not guaranteed, okay? Now, the next thing, when we talk about the other possibilities, excuse me, my son is here again. I'm doing my thing right now, so you're going to have to come back later.
Can you sleep with me?
I will tuck you into bed later on, okay?
Okay.
All right, go to bed now. Love you.
Bye.
See ya.
I'm just getting orange juice.
All right, see you later.
Bye.
Bye. So, more about him when we get to Piaget and Erikson in the developmental unit. So, where was I? Oh, we're talking about a coincidence, okay? So with coincidence, okay, look at this here. This is from an experiment or by the website, Tyler Vigan, I think is his name. I apologize if I'm mispronouncing it. There's a pretty strong correlation between the divorce rate in Maine and the per capita consumption of margarine. So in other words, am I supposed to suggest that if I eat margarine, a butter substitute, that's going to sour the relationships of people in Maine? Clearly not. It's a coincidence. So that's an example of a spurious or an illusory correlation. Illusory, let me write that out here because I know it's not on the slide here. Illusory correlation, okay. It's an illusory correlation which is misleading, or spurious, same thing here. This is just a coincidence because what happens here is that you have so many data sets out there, you keep putting them together, you keep looking for things, you're going to find stuff that seems to correlate. I'd be willing to bet that if you collect data beyond 2009, let's say 2010 and 2019, this relationship falls apart. But in this particular instance, it's pretty close. I'll tell you another example of something when it comes to correlation and causation. This is more of a personal thing. 2 years ago, I was making a Halloween pumpkin with my family. And for no particular reason, I decided to carve this pumpkin right here. And This and I took out my Twitter handle, but it's at John Seymour. It's actually, I think it's on a Fiveable website, something like that. But it's actually on my thing there still. And so I carved this, Inferring Correlation from Causation. I said nothing scares me more. This stupid pumpkin went viral. Had close to like 30,000 likes, I think, on Twitter. So I thought I was going to get maybe like 20. I thought it would have been, get a laugh from a few friends, but somehow that took off. So yeah, sometimes you might see it online closer to Halloween about inferring causation from correlation. And yes, that really was my pumpkin. Really, yes, that is my dining room. In fact, the dining room sitting in here right now. Okay. So remember, the only thing you can use to infer causation is the experiment. Correlations only tell you the how closely related they are, but you can't assume causation, one causing the other. So getting into this correlation thing, correlation is determined by what we call a correlation coefficient. Now the coefficient, it's a number. It tells us two things. One, the direction of the relationship. What direction is it going? Okay, is it going upwards or downwards? Is it one changes, the other changes the same direction, or is it negative where it goes, as one goes up, the other goes down? So when we talk about this, it's positive or negative, we call this. And so it makes sense that the number should also be positive or negative. And there's a quotation marks missing over there. So positive or negative correlation here. It's a number corresponds. Okay, is it a positive? Is it a negative? Who knows? I mean, the number will tell you that. So when you see that positive or negative, it will tell you the direction of the relationship. The second thing is the strength of the relationship. How strong of a relationship is there? Okay, and in this case, the numbers correspond to how much do the dots look like a line? How much do the dots look like an actual line where you can make it out? Now, some of those scatter plots, they were pretty spread out. We couldn't make anything. And some, it was a perfect line. So here, it's a number from 1 or from 0 to 1. And so what you end up getting is a range total from -1 to 1 with what number do you think indicating no relationship whatsoever? What number would indicate to you, what do you think would indicate absolutely no relationship whatsoever? 0. When we talk about zero correlation, 0 meaning none, as in no correlation. Okay, so you put this all together and you have two pieces of information from this. Is it positive or negative? What direction are the data going? And then the number from 0 to 1, how strong of a line is, or how much of a line is it? How close to a line do those dots become? So here I have this number line from 0 to 1 with an arrow going up. And as the arrow approaches 1, the stronger the relationship. So here, it appears like the 0, let's see here, let me just check. So 0 meaning no correlation at all. Okay, I realize that my picture is blocking out one of the scatter plots. But it's basically what's below here is the same exact above it. So Dolores' question, I will answer that in a little bit, but it's not just a strong negative, it's a perfect negative. So I'm going to get to that in just a little bit. So as you go up this number line, the more and more it looks like a line, okay? So weak correlation, moderate correlation, around 0.2 would be a weak correlation, -0.2 would be a weak correlation. A moderate correlation around 0.5. There's no law about what makes something a weak versus moderate correlation. It's generally speaking relative. But look at this here, okay? You see that there's a 0.5 correlation. You see how the 0.5 kind of goes in the upward direction, and the -0.5 goes in the downwards direction. The sign simply tells you the direction. The number tells you how strong how close to a line is, how strong is that relationship. Notice that the 0.5 and the -0.5 look much more like a line than the 0 that you see on the far left screen. Now, going up, we get to the strong correlation of 0.7, 0.8, 0.9, and 1 being, along with -1, being a perfect correlation. Look at 0.9 and -0.9. Notice that, you see how they look more like a line compared to the 0.5, and even more so than the 0? Same thing with -0.9, okay? which, they look very much like a line. And then when you get to 1 and -1, you can see that they are perfect lines. So to Lori's question, you see how -1, it's a straight line. It is you can draw a line, it's easy, there's no variability to that line. It's a straight downwards line. So let me ask you this, okay? Which is stronger, 0.9 or -0.9? Which is stronger? Which is stronger? So we have one person saying 0.9, they're equal. Okay. And the correct answer is it's the same. They're the same strength. Even though you learned in, what was it, 6th, 7th, 8th grade about negative and positive numbers, here it's not like that. Here the sign just tells you the direction. A 0.9 and a -0.9 are the same strength. The sign just tells you the direction that they go, okay? Neither is stronger, okay? Is it always going to be a good thing to have a linear relationship? Well, sometimes you don't want a linear relationship. Sometimes do you want there to be a linear relationship between, I think of something silly. I don't want to say silly, but watching The Bachelor and getting an F on your next test. I mean, do you want that? I mean, do you want that? If there's a strong linear relationship for some reason between watching The Bachelor and failing AP Psych, just because there's a strong linear relationship doesn't mean it's a good thing. It doesn't mean that you don't always want linear. Hopefully, there's no relationship. Hopefully, there's no relationship between eating a certain food and the risk of poor health or something like that. You don't want that. You have to interpret it. Is this a good thing? Is it a good thing that there's a linear relationship between carbon emissions and climate change? I would say no. I would say no. So, okay. I think I got the questions there. Okay, so let me ask you this. Which is stronger? -0.5 or 0.4? -0.5 or 4? 0.4. Which is stronger? Very good, very good. See, it's -0.5. -0.5. Between -0.5 and 0.4, negative. Yeah, so just grab the sign. It's okay. Remember, the sign just tells you the direction. Okay. Let's suppose someone told you that they did a correlation analysis and they found a 1.6 correlation. What are they going to tell you? What should you tell them? Hopefully we're not going to be confrontational about it. We're going to be polite about it. A correlation is a range between -1 and 1. You can't have anything above 1. You can't have anything below -1. They did a mathematical error. And I will tell you this. I have seen it on at least one released AP exam, I believe. I've seen it on so many practice tests. I've seen it. I've seen teachers ask questions about this on the AP Psychology Teachers Facebook group. What is which is the strongest correlation? And they're going to have something that's going to be 1.4, -0.9, 0.87, 0, and -0.1. And clearly the one that's above 1 or below -1 can't be the answer because it ranges from -1 to 1. It can't be, and the correct answer in this case would be -0.9. Remember, the sign just tells you direction. The sign just tells you the direction. Which way does it go? Okay. So, any questions about that? Again, if you have questions, feel free to ask. Okay. So let's revisit some of these scatter plots here. And what are the scatter plots here? Like, what are these correlations here? And again, it is a fair game question that you'll be given a scatter plot and say, what's the correlation of this? And they'll give you choices. I guarantee you it will be relatively easy. Let's say they gave you something like this. And the correlation here is -0.62, okay? They won't give you negative 0.6, negative 0.61, negative 0.62, negative 6.3. They're not going to do that. They might give you negative 0.62, 1.5, 0, 0.4, and the scatter plot would actually be easier than this. It would be much easier. This is not the greatest scatter plot for this. This one here is pretty close to 0, okay? Negative 0.06, that's pretty close to 0 right there. This one, too, is also pretty close to 0 right here as well, okay? This one here is a little easier to discern. Not great, okay, but we said this was kind of in a positive direction. 0.27, again, they'll be pretty easy. This one here is a little misleading. This one here is a 0.61. I guarantee you, and I wish I had better ones for this in terms of what they might give you. Close to the AP exam, we'll have really good examples here, but it would be a pretty, like those things we saw with the mile time and minutes exercising. It was pretty clear. And the scatter plot would be pretty easy. If they give you a 0 scatter plot, it will look like a big just array of dots that you can't make any pattern for. It will be blatantly easy. This one, I think, is a fair game question. I know people already answered it earlier on. What's this one here? What is this one here? 1.0. Rose got it right. Correlation of 1.0, you are correct. Okay, 1.0. And then this one here would be negative 1, okay? That's a fair game question. That is a fair game question. They could ask that. So, all right, so that's correlation. Okay, and if you have any questions about correlation, feel free to put it in there. So, want to get to now talking about basically stuff you talked about before. This is a 100-question multiple choice test, hypothetical data here. And really, I'm going to gloss over kind of quickly. The mean is your average, okay? It's where you add up all the questions and you divide by the number of questions, and you get an average there. Will they ask you to calculate a mean? If they do, it would be simple numbers. It would be simple figures, ones that shouldn't take much time to do. And sometimes ones that you can kind of just eyeball, and you could be able to figure it out. Yes, you add up all the numbers in the data set and you divide by the numbers, and I think I got this right. It's a total of 1137 divided by 15 is 75.8 average. Okay, the median is the middle average. You put the numbers in order, not the middle average, excuse me, the middle number. You put the numbers in order. What is the exact middle number? What is it smack dab in the middle? Okay, what is smack dab in the middle? Okay, and then the mode is the most frequently recurring number. Okay, it's the one that appears most often. Okay, and so we have here these three values: mean, median, and mode. Okay, mean is your arithmetic average. Okay, it's the one that is most easily affected by extreme scores. So if we're all getting like 10-point multiple choice test, and we're all getting 9s and 10s, 9s and 10s, 9s and 10s, and then suddenly someone gets a 0, that can throw the average down. Can there be more than one median? For our purposes, we're going to say absolutely not. You can't. There can only be one middle value. There are some technical things where if it's too spread out, sometimes they report the two middle numbers. But as Lori suggests here, if it's a middle number, let's say there's an even data set, so let's say there's 10 numbers, you would take the average of the 5th and 6th number in this case, and that would be your median. And they wouldn't get any more complicated than that. As a matter of fact, I think, in my opinion, they would probably stick to pretty easy numbers to work with. So your median is the middle value. I apologize, that's a little, doesn't quite come very clearly there. The mode, most frequent value, something got lost in this, I don't know what got lost there, but it is the most frequent value. It is the one that there can be more than one of. You could have more than one mode. You could have more than one mode. Pardon me. Sometimes the data set might not have any mode at all. You could have a data set that goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Technically, the most frequently occurring number is each of them. And you would say there's no mode in that case. There's not one that appears more often than the other. But let's say the numbers were 1, 2, 2, 3, 3, 4, 5, 6, 7, 8, 9, 10. Well, 2 and 3 were tied for the most frequently appearing thing, and you would say, well, there's 2 modes there. Okay, so the mode, there could be more than one there. All right. I have here a fictitious data set. So that's mean, median, mode. Again, if you have questions, feel free to ask in the chat or ask a question. I have here a data set of randomly selected numbers here, supposedly of average IQ. And here, pretend like these are individual value scores, okay? Forget what you see here in this histogram, but assume this is one particular score, assume this is a score, assume this is a score, assume this is a score, and so forth. And it seems to be bimodal, 3 here and 3 here with a sample size of 10. Watch what happens as the hypothetical sample size increases and more data becomes available. Here it is as 100. Here it is as 250. Here it is at 500. Here it is at 1,000, 3,000, and 60,000. Now, I think the reason why these go down here is because of the way the computer classified the numbers. But ignoring that for a moment, what do you see here? What does the shape look like? What does the shape look like? Looking at that slide right there, symmetrical, like a mountain, like a bell curve or a bell, and I agree. So if I were to do an infinite number of, if I were to collect an infinite number of data sets or an infinite number of pieces of data, it would, in theory, look exactly like this. It would look exactly like this, where in this case, the mean is 100, okay? And something called the standard deviation, which we'll talk about in a little bit, is 15. We'll talk more about that later. What's interesting is that because it is symmetrical, this is symmetrical meaning, okay? I have this line right here. What do you think this line represents then? If it's symmetrical and it goes right down the middle, what do you think that line represents? Well, let's put it this way. Because it's the middle value, let's start with this. Because it's the middle value, the middle score. If it's the middle score, what am I referring to there? If it's the middle score. That's correct. It would be the median because it's the middle score. Now, interestingly, the y-axis, okay, this indicates how many there are of this, okay, how many there are of this. Because this is also the most frequently occurring value, this is also considered to be the what? What's this also considered to be? The mode, that's right. In fact, okay, the mode, when you ever see these bell-shaped curves, and they're not always going to look pretty like this, the highest thing there, pardon me, the highest number, which is the highest point in that, curve thing or whatever it looks like, is going to be your mode. Sometimes it's bimodal, in which there'll be a tie for the 2 tallest points. But it's also, as we just said, the median because it is the middle. I apologize again, got cut off there. It is the middle. So this is my median. Again, my picture is cutting it off. It's the middle value there. Okay, it's the middle value. Now, because it's the middle value, what percentage of the population scored below this median here? What percentage of the population scored below if it's the middle? Lori says 50%, and I agree. Okay, so what percentage scored above? What percentage scored above? Lori also says 50, and I agree. Okay. In other words, when it comes to this nice bell curve shape thing here, we see that 50% scored below the median, 50% scored above the median. This whole bell curve, okay, which theoretically goes on forever and ever and ever in both directions, represents 100% of the entire population. And in this case, it's referred to as the normal distribution, in which the mean equals the median equals the mode. The mean equals the median equals the mode. Okay? So, now, let's suppose we have here, it's a IQ, and we have a lot of people who score somewhere in the middle, okay, 100. Normal distribution, mean equals median equals mode. All right, now, This is how I teach students about the following concept, about skewed distributions, which scare a lot of students. I know some teachers don't even teach it, or they gloss over it. I once upon a time used to gloss over it. It appeared on an FRQ like in 2006 or 2007. There was like 2 or 3 points that were relating to skew. So looking at this, what is most affected by, which of those three, mean, median, mode, which is most affected by extreme scores? We actually already talked about this. The mean is most affected. So if I have a few people with a really high IQ, with extremely high IQ, what would happen to what would be pulled in the upwards direction the most? What would be pulled in the upwards direction the most? Skew. Yeah, we talked about this is going to be a skewed distribution, right? Which we'll get to in just a second here. So the mean, okay, is going to be pulled quite a bit to the right, okay? So here we have this value here, okay? This is the x-axis, okay? Where we have some extreme scores that seem to pull the values quite a bit. Now, mean and median and mode are not all equal, not anymore. Now we have a problem here. So what do we do about this, okay? How do we identify which one's which? Well, here's the way I would do it. So if there is a few high positive scores, which is pulled in the most extreme, what is pulled the most? What is going to be pulled the most? Mean, median, or mode? Which will be pulled the most in this direction? Pardon me, I'm sorry. What would you say? What gets pulled the most? The mean, the median, or the mode? It would be the mean, okay? What's always in the middle? What's always in the middle? The median is always in the middle. And what's left over? What do we have left? The mode being left over here. So, okay, it looks, there it is right there, okay? So these, where we had a few extremely high scores, it's pulling it in this direction here, okay? The mean is pulled the most, followed by the median, and the mode is left over. The mean is pulled the most, the mean is most affected by extreme scores, the median is always in the middle, the mode is left over. Now, because there are a few high scores, a few extreme positive scores, it's pulling it in the positive direction, called a positive skew, okay? Sometimes referred to as skewed right. But this is a positive skew. And in a positive skew, the mean equals the median equals the mode. I'm sorry. The mean is the highest value followed by the median, and the mode is the lowest value. Okay. So, I realize the alligator mouths, as it were, that's how I learned the alligator mouths are kind of opposite of what you see here. Still, think about those extreme scores, pulling the mean, in this case, the positive direction the most. Mean is always the middle. What's left over? The mode. But what happens if I have a different scale? Let's say it's the friendliness scale. Okay, how friendly are you? And it's a nice normal distribution. But then Oscar the Grouch comes in from Sesame Street, who's very grouchy and not very friendly. Yes, I know he's had some times where he was pretty friendly, but and now pulls the data in this direction. Okay, what is most affected by extreme scores? What is most affected by extreme scores? Again, the mean is most affected by extreme scores. Very good. So then I ask, what's in the middle? What is always in the middle? The median is always in the middle. Very good. Okay. And then what's left over? The mode is what's left over. And so it looks something like this. So we have a few extremely low scores, some extreme low scores pulling the mean in the negative direction the most. The median is always in the middle, and the mode is, in this case, the highest score, okay? It's over here. It happens to be the highest value on the x-axis here, okay? This is what we call a negative skew. In this case, the mode is the highest value. The median is always in the middle, and then the mean is left over, okay? So, any questions so far? Okay. And it is a little tricky at times, I have to admit. It's something that if you practice doing that, it gets a little easier as time goes on. But still, it's like, wow, oh my gosh, which one's which? Remember, extreme scores, which is most effective, okay? The mean probably is the most effective, okay? Well, it is, okay? The median is always in the middle, and the mode is left over. Is it always like this in practice? No, but for AP Psych, we're going to go with this, okay? Now, here I have 3 bell-shaped curves. They're all normal distributions, okay? Look at that. What do you notice? What do you notice in terms of the, besides the height of the curve, what do you notice? What do you notice in this case? Sort of, yeah. There's much more spread. You're right. Much more spread, okay? So in this case, we are talking about how much spread there is in the data. And here we're talking about measures of spread. We were just talking about measures of central variability, which is the mean, median, mode. Now we're talking about spread, like measures of spread. Okay, Dylan asked a good question. Why is rightward skew positive? Because, I'll go back here for a second. Why is this called a positive skew? Because if the mean was 100, okay, and I have someone with a 500 IQ, Dylan, what does that do to the mean? What does that do to the mean? What does that do to my average? If I have someone with a 5,000 IQ, what does that do to the mean? Pulls it up in the positive direction. Pulls it up in the positive direction. So I think the positive would be this direction, I think, for you. It will pull, that's why it's skewing in the positive ends. Like, wow, the mean was 150. Well, that's because we had a few extremely high scores. It was skewing it in the upwards positive direction. That's why. And then negative, well, it was some low scores skewing in the opposite direction. That's why it's called positive and negative skew. The tail gets the name. The tail gets the name. So that's why we say that. All right, so measures of spread, okay? Without measures of spread, we're actually talking about measures of variation. And there are 2 measures of variation I learned about already, which is the range, okay? Range is where you take the highest score and you subtract from that the lowest score. I think we learned about this at some point. The problem is that this is not a very great type. It's very crude, let's put it this way. Let's say I have 2 data sets, okay? So I have this data set here. Again, got cut off here, and this is going to make a difference. The lowest score is 10, and the highest score is 27. If the highest score is 27, what is the range of this particular data set? If the highest score is 27 and the lowest score is 10, okay, it is indeed 17, the range being 17 in this case. What about this data set here? What about this data set here? Looking at that there, what do you see for that? What do you see for that? But again, what's the range of that? We see a lot of 12, that's true. I guess my question is, what's the range of that data set? The range is also 17. So they both have the same range. But my question is this, does it really have the same type of variation though? When you look at if you were to look at those 2 groups, do they vary in the same way? Do they really vary? Not really, no. I mean, yeah, you have this one person with 27, but otherwise in that one group, it's a lot of 10s, 11s, and mostly 12s. Where in the other group, it's much more spread, right? There's a lot more variation in the left-hand side of group compared to the right-hand side group. So range is a very crude measure, but there are better measures out there. And yeah, 27 is an outlier to be sure, okay? So a better measure of variation is called the standard deviation. The standard deviation, okay? So standard deviation, and I hate doing this, I have put the word standard. Basically, it's a generalized measure of variability that allows you to describe the variation of one data set versus another data set. Like, okay, there's this much variation here versus this amount of variation there. It's a lot more accurate way. Would you use interquartile range for skewed distributions? No, because the reason why I wouldn't use interquartile range is because if you have a series of very extreme, like a number of extreme scores, or put in for a very strong skew, you assume one quartile and the other quartile they are symmetrical, but they're not going to be necessarily. Well, it's an alternative. Let's put it that way. It's not great. It's not a great one. Depends on what you're trying to do with it. Interquartile range also sort of assumes it's nicer when there's a normal distribution, but I wouldn't necessarily say that it is. It depends, much like everything else in psychology. But I also say this, that interquartile range, I would bet a year's worth of salary is not going to be on the AP exam. So, but nevertheless, it's an alternative, but not the best one, in my opinion. But some might disagree with me, and so be it. I wouldn't necessarily. I have not seen interquartile range. I've not seen any textbook. And if you have no idea, everyone else, what I'm talking about, just ignore what I just said for the last couple minutes here. So, all right. So measures of variation, okay, standard deviation. Standard deviation, this is just memorization here. This is just something to understand here. Standard deviation is the square root of something called the variance, and the variance, as a corollary, is the square of a standard deviation. That's as hard as it will get there. You'll never be given a data set and have to calculate the standard deviation, although you might have to eyeball a standard deviation. I'll give you an example in a little bit here. But basically, the only calculations when it comes to standard deviation is if they give you a variance, something called variance. If the variance is 100, what's the standard deviation? Variance is 100, what's the standard deviation? So variance is 100, what's the standard deviation? It would be the square root of the variance. So if the variance is 100, the standard deviation would be 10 in this case, okay? Whereas the variance, let's say the standard deviation is 5. What would be the variance be in this case? What would the variance be? It would be 25. All right. So going back to the application of standard deviation, you might be asked, for example, which one has the highest standard deviation? Okay. Standard deviation, the greater the standard deviation, the more spread there is in a data set. So looking at these three, I'll call them A, B, and C, which of these three would you say has the highest standard deviation? We'll call the one on the upper left A, we'll call the upper right B, and then C is at the bottom. Which one would you say, A, B, or C? Which one has the greatest standard deviation, okay? And the answer is resoundingly C, okay? How we calculate this, you don't have to worry about it. Not for our purposes. It will always be given to you, okay? Again, sorry for my allergies. I really apologize here. It's going to be C. Standard deviation is 15. So if it's a really wide distribution, they might ask you which one has the highest standard deviation. It's going to be the one with the widest distribution. That's a fair game question, in my opinion. So, all right, now it gets fun. And now we're getting into some really fun stuff here. And actually, I'm kind of getting into a different unit, but I still teach it with statistics, and it's this. So in a normal distribution, okay, there's your mean. Okay, mean equals median equals mode. Each of these lines to the left and right represent one standard deviation, either above or below. Kind of debating whether there should be a separate thing, but what I think I will do is, I'm going to talk about it maybe on a different podcast, podcast or stream, I should say, excuse me. It's not a podcast, these are streams. I'll talk about this another time, but I'll still talk about this here. Empirical rule, not sure what you mean by that, but not a term I would use here. I'll tell you where I'm going with this. It's actually z-scores. And if you've taken AP Stat in the past, well, then you know what that is. So here is one standard deviation above the mean. This is one standard deviation below the mean, 2 standard deviations above and 2 standard deviations below, and 3 standard deviations above and 3 standard deviations below. Okay, so here you have how much spread there is. Okay, great, fine, wonderful. Okay, and if it's the mean, Well, it's 0 standard deviations away because the mean doesn't deviate from the mean. There's 0, doesn't spread away at all from the mean. The mean is 0 standard deviations from the mean. So if put it in one way, if the mean is 100 and the standard deviation is 15, if I scored 115, my score is 1 standard deviation away from the mean, okay? Now, this is where it gets kind of interesting. Suppose, okay, I want to come up with something where it's a real mouthful to talk about this in such a way here. 1 standard deviation of the mean, 2 standard deviations of the mean. What if I came up with a way to better describe this, okay? And what I start doing here is that when it's 1 standard deviation of the mean, above the mean, I'm just going to call it +1. 2 standard deviations above the mean will be +2, +2. 3 standard deviations above the mean, +3, okay? If it's 1 standard deviation below the mean, I do apologize, these numbers look like that, but 1 standard deviation below the mean is -1, -2, and -3, okay? And so what am I doing here? I'm kind of giving a number to correspond to standard deviations away from the mean, either above the mean or below the mean. That's what I'm doing here, either above the mean or below the mean. This is a much better way of saying it than 2 standard deviations below the mean. It's less of a mouthful. So I'm going to give this a name. I'm going to call it the z-score. Why we call it a z-score? I can't tell you why. It's cut off here. I do apologize again. So I'm just going to type it here so you can see it. The z-score. The z-score simply tells you, okay, number of standard deviations above or below the mean. And by the way, the stuff I'm getting into here might be one question on the AP exam. It's inevitable, I suppose, eventually there'll be an FRQ, and there'll be like 3 or 4 questions about maybe. Who knows? I don't write the AP exam. I have no knowledge of it. What would be the z-score of the mean? Let me ask you this. What would be the z-score of the mean? Seeing what you see here, what would be the z-score of the mean? We have Dylan who says 0. That works. Z-score is what it's called because it's short for standardized score. See the Z in there? Is that what you were taught to remember it, or is that? I've never heard that before, but works for me. Does work for me. The Z-score for the mean, okay, would be, in this case, as Dylan says, 0. Okay, it would be 0. So, or if that's something that is just to help us remember, great. That's wonderful. If it's something you're taught, I'd like to know about that. Either way, it works for me. So, again, the z-score it seems so intimidating. It just tells you number of standard deviations away from the mean, above or below. So, how do you calculate the z-score? In some ways, you kind of eyeball it, but the z-score, for some reason, is something got cut off here. It's the score, whatever your score is in question, minus the mean. So I'm going to actually retype this so it's a little easier to see. The score, or the value, minus the mean, divided by the standard deviation. Okay? So look at this question here. If the mean of a test score, of test scores was 100, and the standard deviation was 15, what would be the z-score of a person who got 130? Give me a moment to look at that there. What would be the z-score of someone who got 130? What do you think about that one? What would it be? Give me a moment to think about that. Lori says 2. Jess says 2. Abigail says 2. Dylan says 2. Yeah, and they would not give you ridiculously complicated numbers for this if it appears. And the answer is 2. Okay. So yeah, this is fair game in AP Stat. You're going to see this a lot in AP Stat. The answer is indeed 2. If this appears in AP Psych, it's one question. I think I've seen it once in released exams. So, but here it kind of lends itself to something else, okay? Notice I have here the standard normal curve yet again, and now I have the z-scores at the bottom. As a quick review, what percentage scores above the middle line? What percentage scores above 0? What percentage scores above a z-score of 0? What percentage is above this from here onwards, from the middle to the far right? 50%. That's correct. 50%. How about from the middle to downwards, or towards the left to infinity? What percentage would that be? Also 50%. So it's a 50-50 split. So far, so good. Well, what about in between? Let's see here. So what does the z-score show? Basically, so what that could tell you is this. Given a set of scores, how well did you do compared to everyone else? If your z-score is 2, that tells you that you scored 2 standard deviations above the average. Now, that by itself doesn't tell you a whole lot, but you're going to find out in just a bit. It tells you a little bit. Knowing that value, it could tell you something else, which I'm going to lead to in a kind of indirect fashion. So stick with me here, you'll see. So here's my curve, my normal curve here, okay? What percentage is between 0 and +1? To get that number, you have to do some fancy calculus, which is not part of this course. You don't need to know it. As a matter of fact, I don't know it either. So I'm just going to give it to you like every other textbook gives it to you. The percentage of the population that got between 0 and 1 is going to be 34%. 34%. Now, because it's symmetrical, because this is a symmetrical bell curve, what does 0 to -1? What will the percentage be from 0 to -1? What would that be? Also, 34%. That's right. Okay. And these are numbers you just have to memorize. Between 1 and 2, 13.5%. -1 and -2, 13.5%. And between 2 and 3, okay, 2% each. And these are numbers that you kind of just have to memorize. If you do 50, 50, 34, 13.5, and 2, if you memorize those numbers, it'll be much easier down the road. Practice it, quiz yourself on it. Eventually, you get to be pretty good at it. Okay, so that's where you get it from this. Yeah. And no matter how flat the normal curve is, as long as it's a normal curve, yes, these are the percentages, okay? Some textbooks might call it 34.1 and 13.5. For AP Psych, this is close enough. Now, what do I do with these numbers? Well, let me ask you this. If, let's say I got a z-score of 1, okay? So mean is 100, standard deviation is 15. I got a 115 on the test, and that gives me a z-score of 1. What percentage scored below me? What percentage scored below me? If this is my score at +1, okay? If my score is at +1, what percentage scored below me? If you're taking AP Stat, this should be fairly easy. Yeah, that's one way of doing it. Not the best way because it goes somewhere here. So Dylan tells us about maybe 84.5%. Maybe agree, disagree, confused maybe, and that's okay if you are, because this is a pretty complicated concept. And I tell you that this can be intimidating to some psychology teachers too, because this is, a lot of psychology teachers weren't trained in psychological science. That's not, their fault. I mean, some states, they say that you can teach psychology if you have credentials, then it has nothing to do with psychology. So it's not their fault. But when they're first learning this or first getting this for the first time, they might be learning for the first time as you. So here's what we're going to do. So basically, from 0 below is 50%. Okay, from 0 to 1 is 34%. Well, what's 50 plus 34? It is Either we're all asleep or 84%, okay? So in this case, it would be 84%, okay? So your percentile, okay, this is what we call percentile. Percentile is what percentage of the population did you outscore? What percentage of the population did a particular value outscore? And what you do here is you go back to this here, and you figure out the z-score. And if this does appear in the AP exam, they will give you such easy numbers that this is all you have to remember. Stats, a different story. Stats, they give you tables to work with and everything else. If your z-score is 2, okay, I just add up everything to the left. 50 plus 34 plus 13.5 gives me 97.5, 97.5 percentile. Percentile is the percentage of people that I outscored. That's correct. Percentile tells you what percentage of the people did you outscore. If you scored the 98th percentile, that means your score outscored 98% of the other people who took the test. That's what that means. Okay. There's no such thing. This percentile is always less than. I'm not sure what you mean by that, Lori, if you can clarify that question. Because if I say I'm at the 85th percentile, what you're saying here is you outscored, it means 85, well, let's put it this way. If I'm at the 85th percentile, it means that 85% of the test takers have a score that's less than mine. But I'm not sure if that clarifies the question or not. So I'll let you, if you want to clarify that question, you can put it in there and I'll go back to it. I'm going to go to the next concept, but I will go back to that original one if you want to clarify that, Lori. So let's see here. Changing gears a little bit, again, Laura, if you want to clarify that question, feel free to put that in there. I'll be happy to answer it. Let's suppose, and here I am, a younger version of myself, about 10, 12 years ago. Would you ever add up values on the right? So the question is, would I ever add up values on the right for percentile? No. You might add up values on the right if you want to know what's scored below you. Like, or let's say, I'm sorry, if you want to say what's scored above you, I mean, you could do that if you want, which is really just the same as adding up below you and subtracting from 100. I mean, if you wanted to just for interest, you certainly could, but in terms of percentile, it wouldn't really be a relevant thing. So, so here I have this silly new study. I think that if you get a motivational talk before you take your state standardized test in Pennsylvania, it's called the Keystone. I think you'll do better on your test. Okay, so I run this. Thank you very much. It was Halloween on this day. As a matter of fact, you know what? If I do a stream close to Halloween, I might wear this hat again because I have it downstairs somewhere. So there's an incentive. Not much of an incentive, but hey, better than nothing. So let's say I do this particular. Let's see. I'm sure if you look long and hard enough, you will find this out there somewhere. So, I will wear it the whole live session, even though it'll probably get pretty hot in that hat. So, anyway, so I run this ridiculous study, and yes, I'll wear it if I can find it. So I collect data, okay, and it looks something like this, okay. Did my study work? Yeah, there's a huge Twitter campaign right there. 5-able bat hat 2K19. That'll get the attention of about what, 6 people maybe. So, did my study work here? Did my motivational talk? Maybe the hat was distracting. Did my study work? Oh, this is the mean. So this is the regular data here. Here's the means at the bottom. I pointed that out here. Does it look like it worked? Does it look like it worked? What would you say? Did my motivational talk produce an effect? No, it did not. Did it change the scores? No, it certainly did not. Okay, that's pretty clear. What about this here? Let's say it's a different study. Did my motivational talk work here? There, it becomes pretty clear. Yes, it did. Here we have a 5-point difference, over a 5-point difference, but if you look carefully, you'll see that in the motivational speech condition, there was an outlier, an extreme score. Does that make a difference? Could I say that there is a difference between the groups? Well, there's a difference, but is it a big enough difference? Is it a difference where I can be confident to say that there is a difference? Well, I don't know. And now it's not so clear. What about this here? Here I have a 0.2 difference. Is there a difference? Yes. Is it one that I should be very excited about and say, yes, it makes a difference? Probably not, okay? Probably not. But the question then becomes, when do I say, yes, there is an effect? When can I be confident to say, yes, there is an effect? Well, it depends. It depends on what statistics say. Let me give you an example here. Let's suppose I collect some data, and I do this. I say, after collecting data, after analyzing the data, I believe there is a difference, but I might be wrong. But I'm pretty confident that there is a difference, but I might be wrong. Well, let's change the setting here a little bit. Let's forget about this for a moment. Let's put this aside for a moment, and let's give an alternative here. And the alternative would be this. Let's pretend like I'm not doing the study. Let's pretend like that's not happening. And instead, let's say I collected data, and this data tells me something. And based upon the data that I have received, I make the following claim. I believe that there is cake outside. Right outside of your house or wherever it is, there's cake. Okay? I think there is cake. I hope you like cake, because I think there's cake. Now, hopefully that's pretty exciting. But all I'm saying is what? I think there might be cake. I might be wrong. So here I have a picture of some cake. Okay? What have I claimed? What is the claim I'm making here? So what am I saying? What am I saying in this analogy here? What's the claim I'm making? What have I claimed? What am I saying here? I am saying that there is cake. Okay? All right? I am saying that there is cake. That's all I'm saying. I do not say, okay, yeah, you can have your cake, you need to let there be cake, or let them eat cake. Yes. I'm not saying there's a lot of cake. For all I know, there could be a huge wedding cake out there. Or it could just be a few morsels. I don't know. All I'm telling you is that I'm confident that there's cake. Don't know how much, just that there's cake. I don't know if it was well made. I don't know if you followed the directions. I don't know if you used, fancy tools to make the cake. I don't know if you used electrical equipment or if you used, if you mixed the batter by hand. I don't know. All I know is that I'm confident that there's cake. Can't tell you anything about it. I can't tell you if it was made by a famous chef. I can't tell you if it was my 6-year-old who made it for a bake sale for the PTO. I can't tell you that. I don't know. My only claim is that there's cake. I don't know if it was used. Yeah, that's right. Don't quite. It's just cake. Okay, and I'm going somewhere with this, I promise you. I can't tell you if I follow the health department's rules about making cake so that it's sanitary, so that it's safe to eat. I don't know. I don't know if it tastes good. For all I know, I might have substituted salt for sugar and it tastes lousy. All I know is for sure is that there is cake. I could be wrong, but I'm pretty sure there's cake. Okay? Well, so the only thing here in this analogy, all I'm saying here is that I am pretty confident that there is the existence of cake. Okay? And the reason why I kind of go to this great length is because this is where I talk about a difference. I say that in this set of data, going back to my fictitious motivational talk study, I claim there is a difference. I claim there is a difference between the groups. I claim there is an effect. Now, what am I claiming here? What am I actually claiming? I am claiming that there is an effect. I am claiming that there is an actual effect of some kind. How much of an effect? I don't know. Okay? All I'm saying is there's an effect. I don't know if it's a huge difference between the two groups. Could be a huge difference. It could be a small difference. But I am sure that there is a difference. I am sure there is an effect. I don't know if it was a well-designed study. It could have been a terrible study. It could have been a great study. All I know is that I'm confident there's a difference between groups. I don't know if it was done. The study was done by a fifth grader doing a science fair project for a school, or if it was done by Philip Zimbardo of Stanford University. I don't know. All I can tell you is that in this set of data, I am absolutely confident that there is a difference, that there is an effect. I don't know if the research was ethical or not. I don't know. I don't know if it will make an impact in the world. I don't know if it will change the world or if no one will care. All I know is that there is an effect. I am claiming that there is an effect, but I could be wrong. I'm pretty confident, though, that there is an effect. And you see, and the reason why I'm really harping on this is because this leads to a concept that students across the board get very confused all the time. Okay? You see, here I'm making this claim, okay, that there is an effect. I could be wrong, okay? I conclude that the effect or the difference exists, but I could be wrong. What happens when I conclude when there is an effect or a difference that exists and I am wrong? Now, if you've taken AP Stat, then you know perhaps where this is going. We call this in research, we call this type 1 error. We call this a type 1 error. When I claim that there's an effect and I'm wrong. Now, how do I actually prove whether or not I'm right or wrong in the long run? This is all theoretical, and just stick with me here. This is me saying that there is an effect and I'm wrong, okay? We call that type 1 error. Every study that's conducted in psychology always will have a chance of there being type 1 error. Every study will have a conclusion. If we say we found a resounding difference, there is still a chance that their claim is wrong. Okay, now if you take AP Stat, this gets a little easier to understand how they get to this idea. But here it's more of a definition that we have to understand here. And the chance of this happening is called a p-value. It means the probability of these two things happening here. What do we call it? What's going to happen here? What's the chance that I'm wrong? If I make this claim that there's a difference, much like if I say, if I make a claim that there's cake, what's the chance that I am wrong? Well, there's something called the p-value. How you calculate the p-value, beyond the scope of the course. But you might be given a p-value and you might have to interpret the p-value. So, how do we do this? Well, let's say, for example, okay, I have a 0.95 chance of being wrong. I have a 95% chance of being wrong. Would you want to take the risk of being wrong at 95%? Let me up the stakes here for you. Let's suppose I said, if you're right, we're going to give you an A in AP Psych. But if you're wrong, you're being expelled from school. Do you want to take the chance with a 95% chance of being wrong? What do you think? You think a 95% chance is worth it? What do you think? Would you want to take the risk of being wrong with a 95% chance of being wrong? I know that if answering this question was meant a job promotion versus being fired, okay, would I want to risk it with a 95% chance of being wrong? If I'm wrong, I get fired. If I'm right, I get a promotion. If I'm with a 95% chance of being wrong, guess what? I'm not going to take that chance, okay? It is way too big of a risk, okay? What about 75 or 50% or 25% or 10%? Well, now I'm getting a little bit more confident here as those numbers get lower. As that p-value goes down, I'm getting a little bit more confident, I guess. Maybe it's worth it, maybe it's not. What if it's 5% chance of being wrong? What if it's 1% chance of being wrong. What is an acceptable p-value? Okay, for me to make the claim knowing I might be wrong. What is an acceptable risk? Dylan says 5%, and you are correct. For AP Psych, and this is not a law, this is not universal, and there are some people who argue against this, but, okay, a p-value of 0.05 or less is considered to be acceptable, okay? If your p-value is less than 0.05, we call that statistically significant, a statistically significant effect. Meaning, okay, when there is statistical significance, it means that I am confident that the difference or the effect exists. Again, I apologize. I'm going to make sure that I get this correct the next time. That the confidence exists, that the difference exists, okay? When there's statistical significance, it means that there's low type 1 error probability. It means there's a small chance that I am wrong in making this assertion, okay? Many textbooks, many teachers, and on the AP exam, they will also accept this here. The difference was not due to chance, okay? Not due to chance. I have my Mr. Yuck symbol that's kind of blocked off by my picture here, but not due to chance is technically wrong. Your teachers might teach that to you. Your book might even say it is technically wrong. They will accept it on the AP exam. That's why I put it on here. I don't like it's on there. Why this is technically wrong is about a 17-hour stream that no one's going to watch. So I just put there saying, okay, it's there. Take it for what it is. P-scores help to improve the confidence that there is causation shown in data. So if I'm doing an experiment, okay, I find a difference, okay, between the two groups after an independent variable manipulation. There's a difference between the two groups, control and experimental, in my dependent variable. The lower the p-value, the more confident in my assertion that I am correct, or the more confident I am in saying there is a difference, there is an effect, okay? I can't tell you how big of an effect. I can't tell you how much of an effect. I can't tell you if the study was ethical. And the reason why I was kind of harping on this is because in the past, on FRQs, on the multiple choice, they've asked questions like this about what does it mean when something is statistically significant? And one of the choices might be the difference between the two groups was large. You don't know that. You just know that there's an effect. You don't know how large. You don't know anything about the if the study was ethical. You won't be able to know if it was a meaningful study. All it tells you is how confident we have to be, or can you be in making the assertion that the effect is there. You will not have to calculate the p-value. AP Stat, there's a way of ascertaining it. Here for Psych, they say p equals 0.75. Is that statistically significant? You're going to say no, because 0.05 is the acceptable level here, okay? So that's statistical significance, okay? You will not have to calculate a p-value or anything like that, but you will have to interpret a p-value. And when you start practicing for the AP exam, you'll see that they've asked about statistical significance numerous times, okay? Really quickly, what I want to do here is this last slide. Two statistics I want to talk about. This is if I want to compare two groups. I know we are running late here. If I'm comparing two groups, SAT scores, let's say, okay, and these are the two schools I teach at, or I teach at Cheltenham High School, and one of our local schools is at Upper Dublin. If I want to compare Cheltenham versus Upper Dublin, and their average SAT scores, okay, is there a difference between the two? The type of test I want to run, okay, if I want to compare the two, is called a t-test, okay? And a t-test, and it's cut off here again, I apologize. The t-test, okay, I'm going to type it here so we see it. The t-test, okay, compares exactly, the means of exactly two groups. Exactly two groups. So Cheltenham had 1550 average SAT, and Upper Dublin had 1530. And no, they're not that high. I'm just, totally making up numbers right now. Is that statistically significant? A t-test will tell me that. Do you have to calculate a t-test? No, it's more like know what a t-test is. And further, if I want to compare more than two groups. Why more than two groups? So we have Cheltenham, Upper Dublin, and Abington. By the way, if you take a push, or you learn about the constitutional court case where public prayer in school was declared unconstitutional, or school-led prayer was unconstitutional, that was Abington, or Shemp versus Abington. That would be this Abington here. It's the next school over from where I am. A little cross-curricular connection there. Anyway, if I want to compare the means of the three groups there, of the three schools, okay, this is something called ANOVA. ANOVA, and it's ANOVA, again, gets cut off there, okay, compares the means of three or more groups. Why that is beyond the scope of this course, but understand the difference between the two there, between the ANOVA and the t-test. So I went through a lot of statistics. This is something that I spend maybe a week to a week and a half talking about, and here I am putting in just a little over an hour and a half, and I realize that's a lot to digest. And if you've never or haven't been familiar with these statistics before, if you're able to watch the replay of this, maybe you can look at it a couple times, and kind of get an impression here. Are there any questions I can answer about statistics? I know here in the East Coast it's 9:30, and you should be getting to bed soon, I hope, so you get a good night's rest for tomorrow. If you're out on the West Coast, well, I guess you have dinner's almost ready, I suppose. But any questions I can answer, anything at all. As my best man at my wedding said, he's a teacher too. He would actually say questions, comments, insults. Save the insults for not now. Type 2 error. So I'm going to answer this to Lori, and if you're confused or if you hit your saturation point, please ignore what I'm about to say. Type 2 is where you say no effect exists, and it's actually true. So I say there's no difference. There is no difference. Turns out to be true. That's called type 2 error. Not on the AP Psych exam, I don't think. That's why I'm only covering type 1 error. But yeah, type 2 error is the exact opposite, as it were. Okay, no problem.